Hello and welcome to this lecture on antiderivatives. The goal of this lecture is to compute some integrals by hand without using partitions, upper sums, and lower sums. The method we're going to use is a consequence of the fundamental theorem of calculus part 2. This part is sometimes called the evaluation theorem because it gives us a way to evaluate integrals without using Riemann sums. So what it says is, if capital G is a differentiable function whose first derivative little g of x is continuous on the closed bounded interval from a to b, then capital G of b minus capital G of a is equal to the integral from a to b of little g of x dx. The way this is phrased, it sounds like a statement about capital G, but let's reinterpret this as a theorem about little g. Suppose I have some continuous function from a to b which I'm trying to integrate. So that's little g of x. If I can find a function capital G whose derivative is little g, then this integral from a to b of little g of x dx is capital G of b minus capital G of a. A function whose derivative is little g is called an antiderivative of little g. So what the fundamental theorem of calculus part 2 tells us is that if we can find an antiderivative for our integrand, then we can evaluate this definite integral just by plugging the endpoints into the antiderivative. We're going to use the following corollaries to the mean value theorem on the first example. So actually, let me go ahead and go forwards. We'll look at the first example, and I put the two corollaries here as well. Okay, so these two statements were consequences of the mean value theorem. The first one says, if g is differentiable on, say, the closed bounded interval from a to b, and its derivative is 0, then g itself is a constant. The second one says, any two functions which have the same derivative differ by a constant. So in particular, let's say their derivative is a function we call little g of x. If I find some antiderivative of little g, and you find a different antiderivative of little g, our selections are not very different. Yours would be mine plus a constant. So it's not like one antiderivative can look like sine of x squared and the other one is going to look like natural log of x cubed or anything like that. Those would be very different functions. If I have an antiderivative like sine of x, yours might look like sine of x plus 5. Okay, now let's integrate from 1 to 4, 0 dx. Okay, so here, g of x from the statement of the fundamental theorem of calculus part 2 is 0. We need a function capital G of x so that g prime is little g of x, which of course is 0. According to number 1, g of x is constant. Let me pick g of x equal to 7. You could have picked a different constant, but the difference between any two constants is itself a constant, satisfying number 2 up here. Okay, so by the fundamental theorem of calculus part 2, the integral from 1 to 4 of little g of x dx will be capital G of 4 minus capital G of 1. Therefore, the integral from 1 to 4 of 0 dx is equal to 7 minus 7, which of course is 0. That's an unsurprising result because how much area sits under the function with height 0? 0 area. So geometrically, we anticipated this result. Now you could have picked a different antiderivative. You could have had g of x equal to 10 or g of x equals negative 5 or something like that. You could pick any constant to be the antiderivative capital G of x. Regardless of the constant you pick though, when you did capital G of 4 minus capital G of 1, you would get 0. Okay, I wrote out several steps here. Once you get the hang of this, you don't usually write that out. So let's go through 3 examples on one slide. Now let's integrate 3 from 1 to 4. Again, geometrically, that's like, what's the area under the function whose height is 3 from 1 to 4? Well, that's going to be height 3, base 3. The answer is 9, but let's see how to get this using the fundamental theorem of calculus, part 2, the evaluation theorem. Okay, in the language of the theorem, g of x is 3. I need an antiderivative. So I need to think of a function whose derivative would be 3. 3 is a constant derivative, so that's like, what function has a constant tangent slope of 3? 3x. If you differentiate 3x, you're left with just 3. So the integral of 3 from 1 to 4 is going to be g of 4 minus g of 1, which is 3 times 4 minus 3 times 1, or 12 minus 3, which is 9. You could also use something like g of x equals 3x minus 100, 3x plus 17. It doesn't matter. If you use any of these antiderivatives, you'll still get 9. So I recommend you pick the simplest version. Okay, let's look at the second example on this slide. Little g of x here is 2x. So thinking backwards, what function could I differentiate in order to get 2x? Well, here, if you kind of think of undoing the power rule, you might get to capital G of x equals x squared, or x squared plus 1, or x squared minus 4. But again, there's no reason to add a constant onto this in order to use the evaluation theorem. We can now say that the integral of 2x from 1 to 4 will be g of 4 minus g of 1, which is 16 minus 1, or 15. And you could work that out geometrically as well, because 2x from 1 to 4 is going to give you something that looks, I think, like a trapezoid, right? But here's, I think, a faster way. Okay, let's look at the last example. Here, the integrand function is x squared. What's an antiderivative for x squared? Well, look what happened in the two examples above. We differentiate 3x to get 3. We differentiate x squared to get 2x. What would we differentiate to get x squared? Well, it would be kind of like x cubed. But if I differentiated x cubed, the 3 would come down and I would have 3x squared. So instead of x cubed, let's do 1/3 x cubed. Now if you differentiate that, the 3 comes down, cancels out the 1/3, and we're left with x squared. Therefore, the integral from 1 to 4 of x squared dx is going to be 1/3 4 cubed minus 1/3 1 cubed. That simplifies to 63 over 3, which is actually 21. When we defined differentiation, we used a difference quotient. We actually had a formula for a derivative. What a derivative was falls out of the difference quotient. Antidifferentiation doesn't really have that. So we don't have some kind of limit of a difference quotient that we take in order to pass from a function to its antiderivative. So on the one hand, it might be harder. On the other hand, it might be actually more fun. You kind of have to put a puzzle together. Luckily, we do have some properties of antidifferentiation which follow from properties of differentiation. So suppose capital F prime is little f and capital G prime is little g. So capital F is an antiderivative for little f and capital G is an antiderivative for little g. Then what would be an antiderivative of little f plus little g? Well, differentiation splits across addition and subtraction, and so does antidifferentiation. So an antiderivative of little f plus little g would just be big F plus big G. Whenever you take an antiderivative, you can turn around and differentiate it and see that you get back what you were trying to antidifferentiate. So if I took the derivative of capital F plus capital G, that would just be capital F prime plus capital G prime, which is little f plus little g. So if you're looking at something that has several terms added or subtracted together, you can just do them term by term. Similarly, an antiderivative of 3 times little f of x would just be 3 times capital F of x, because that's how differentiation works. The derivative of 3 capital F is 3 capital F prime, or in other words, it's 3 little f of x. With these two properties in mind, let's compute the integral from 0 to 2 of the polynomial 4 minus 5x plus 4x cubed with respect to x. Okay, so following the conclusion of number 1, we can just do this term by term. What's an antiderivative of 4? What would we differentiate to get 4? 4x. Again, there's no reason to tack a constant onto that. The next term is minus 5x. Because of the conclusion of number 2, I'm going to leave the minus 5 alone, just ignore it. An antiderivative of x would be 1/2 x squared. And then lastly, 4x cubed altogether actually has a nice antiderivative. That would be x to the 4th. Okay, so we put that all together, and an antiderivative of the whole expression 4 minus 5x plus 4x cubed would be 4x minus 5 times 1/2 x squared plus x to the 4th. So now, according to the fundamental theorem of calculus part 2, the area under the curve y equals 4 minus 5x plus 4x cubed between 0 and 2 is exactly 4 times 2 minus 5 halves times 2 squared plus 2 to the 4th minus 4 times 0 minus 5 halves times 0 squared plus 0 to the 4th. And if you add all that up, it's actually 14 square units of area. Okay, now that we've done a few examples of using the fundamental theorem of calculus part 2 to evaluate these integrals by way of an antiderivative, I want to go over some notation. Then we'll summarize the power rule for antiderivatives that we've actually seen in play a couple of times at this point. I'll use the new notation in the example at the bottom, and then we'll go on with some more antiderivatives. Okay, so when we're looking at an integral from a to b of g of x dx, I've used this word a couple of times, but now we'll state it explicitly. The function you're integrating, little g of x, is called the integrand. It's kind of like what you take the square root of is called the radicand. Not a word I say very often, but I think that's what it's called. The notation dx is called the differential. It's telling you what variable you're integrating with respect to. So here, this is integration with respect to x. It's not ambiguous often when you're integrating functions of one variable, but if you're integrating functions of multiple variables, it could be. And what this g of x dx represents actually is when we pass from the Riemann sum to this integral expression, what the differential is a representation of the width of the rectangles with respect to any partition. So g of x is like the height, dx is like the width. So this is really saying sum up those rectangles. We are integrating from the lower bound a to the upper bound b. It's not always the case that a is less than b, although it usually is. On the right-hand side, capital G of x is our antiderivative. We don't normally write it as g of x. We normally write out what the antiderivative is. I'll do that at the bottom when we go to that example down below. And then I want to introduce in this notation here I sometimes call the evaluation bar. This bar says how and where to evaluate the function g of x. In particular, written this way, this expression means first compute g of b and then subtract off g of a. Now, if you look back at the examples we've already done, we've alluded to the power rule, which says that if you have x to the p, where p is not equal to -1, then the general antiderivative of that would be x to the p plus 1 divided by p plus 1 plus a constant. Now you want to check that if you take the derivative of that, you get back x to the p. So the derivative of 1 over p plus 1, x to the p plus 1 plus c, according to the regular power rule for differentiation, the p plus 1 comes down, cancels out that denominator, we're left with the power of p plus 1 minus 1, and then plus 0. So that simplifies to just x to the p. That tells us that we have the right antiderivative. Okay, so now let's run through this example down here where we have many terms added and subtracted together. I've got some constants in there, so we'll use those two properties of antidifferentiation that we already talked about, and then we'll use the power rule in every term. By the power rule, the antiderivative of x to the fifth is 1 over 6 x to the sixth minus 3 times 1 over 4 x to the fourth plus 5 times 1 over 2 x squared plus, now for the square root term, I want to think of that as x to the 1/2. So that's going to be, let's see, if I add 1 to that, x to the 3/2, and then 3/2 would drop down. So I need to do 2/3, but then multiply that by the 2 out front. So the coefficient has to be 4/3. When in doubt, differentiate that, see if you get back to x to the 1/2. Then the next term, 1 over x cubed, I can rewrite that as x to the -3. So for the power rule for antidifferentiation, that's going to be x to the -2. Then I got to cancel out that -2, so with a coefficient of -1/2 out front, and then minus 7x. Then I write my evaluation bar to say that we're going to integrate this from 1 to 5. So written this way, we're going to plug in 5, subtract off plugging in 1. And if you do that in your calculator, because this is way too hard to evaluate by hand, you get that the area under our integrand function between 1 and 5 is approximately 2,182.05 square units of area. Now notice here in the power rule, p is not equal to -1. For one thing, if we tried to plug that into the formula, we would have a denominator of 0. So in the next example, let's talk about how to integrate x to the -1. This first example is the exception to the power rule. Notice here that the integral from 1 to e of 1 over t dt is like 1 to e t to the -1 dt. That's the exception to that general power rule antiderivative form. And the reason why is that its antiderivative is not a polynomial type expression, it's natural log of t, evaluated at e minus evaluated at 1. So that's natural log of e minus natural log of 1. So that's going to be 1 minus 0 is 1. I just said natural log of t here because the domain of integration was entirely positive, but as a remark, the general antiderivative of 1 over t is not just natural log of t, but it's actually natural log of the absolute value of t plus c. Let's check this. If t is less than 0, then the natural log of the absolute value of t is like saying take the natural log of the positive form of t. In other words, take t and make it positive. So for a negative value, that's like multiply it by -1. Then ddt of natural log of negative t would be 1 over negative t times -1 by the chain rule. So that's 1 over t. Okay, so for example, if I wanted to compute the integral from -10 to -2 of 1 over t dt, then that would be natural log of the absolute value of t evaluated from -10 to -2. Now I plug -2 in first. I get natural log of the absolute value of -2 minus natural log of the absolute value of -10. In other words, natural log of 2 minus natural log of 10. That's going to be a negative number, but that makes sense because over in the third quadrant, 1 over t is below the x-axis, so everything between the graph of this function and the x-axis is going to consist of negative area. And if you wanted to, you could also say that's natural log of 2/10. In this problem, I switched to doing an integral with respect to t. It doesn't matter. 1 over t dt is the same thing as 1 over x dx. And in the next problem, just for fun, I switched to w. So let's integrate from 0 to 3 pi, sine of w dw. So this is doing the same thing as if we integrated from 0 to 3 pi, sine of x dx. For this one, I'll write out the functions like I was doing on the first few examples. The integrand is like our little g of x from the evaluation theorem. That's sine of w. What function has a derivative of sine? You might think cosine, But that's actually not correct. You have to be careful here. Cosine's derivative is negative sine. So the antiderivative we're looking for here is capital G of W is negative cosine of W. You can check yourself. Capital G prime of W is negative the derivative of cosine, but that's negative sine of W, which of course is just sine of W. Okay, so to evaluate this integral, we would say that an antiderivative of sine of W is negative cosine of W, and then we're going to evaluate it first at 3 pi, and then at 0, which we'll subtract off. So this is going to be negative cosine of 3 pi minus negative cosine of 0. Cosine of 3 pi is negative 1. So negative cosine of 3 pi is positive 1. Minus cosine of 0 is 1. So negative cosine of 0 is negative 1. So we're going to minus negative 1. Let's see. In other words, that's plus cosine of 0. I'm getting a little bit confused. So anyway, I think this is 1 plus 1 total area under sine of W between 0 and 3 pi is going to be 2. Okay, let's look at a couple more examples. Let's compute the integral from a to b of e to the 4x plus 2. So once again, I'll identify little g of x is e to the 4x plus 2. What function would we differentiate to get that? That will be our antiderivative capital G of x. Differentiating an exponential function is easy. The exponential part doesn't change. So if I had e to the 4x and I took its derivative, I would get e to the 4x times 4 because of the chain rule. So I need to cancel out that times 4 by multiplying out front by 1/4. Okay, so now if I differentiate 1/4 e to the 4x, I land on the first term, e to the 4x. Now plus, by the power rule, I could think of that as 2 times x to the 0, right? So the antiderivative of 2 is 2x. You start to recognize these. So that's the antiderivative I'm going to use. No need to add a constant. The antiderivative of our integrand is 1/4 e to the 4x plus 2x. So to evaluate this integral, I'm now going to plug b into that first and then subtract off plugging in a. So this would be 1/4 e to the 4b plus 2b minus 1/4 e to the 4a minus 2a. Another common mistake is if your antiderivative consists of multiple terms, when you subtract off, plugging in the lower bound, not distributing the negative. So just watch out for that. This next example looks really exotic, but really each of these terms is a derivative which you may remember. We didn't see them too often. So here our integrand little g of x, I'll write it as 5 times 1 over 1 plus x squared minus 3 times secant squared of x. I think we might have just seen each of these once. So I'll go ahead and remind you, capital G of x here would be 5 times arctan of x minus 3 tangent of x. The derivative of tangent is secant squared. All right, so that's going to be 5 arctan x minus 3 tan x from 0 to pi. This is actually not a good example because tangent has a vertical asymptote, so we're not looking at a continuous integrand. Let me just adjust this to be pi over 4. Our fundamental theorem of calculus part 2. Notice little g of x is continuous across the entire domain of integration. That's actually stronger than you need, but you can't have things like vertical asymptotes occurring in the middle of your integration. You can't just ignore those. So the reason why I just changed the upper bound here from pi to pi over 4 is because tangent has a vertical asymptote at pi over 2. So we would have a point between the lower bound and upper bound where our integrand was not defined. Not only was it not continuous, it wasn't even defined. We'd be looking at shooting off to infinity, perhaps collecting infinite area around there. So we'll deal with that later. That's called improper integration. But for now, because we're just applying the evaluation theorem, I've changed the upper bound so that we can use it. Okay, so then you would plug in the top bound, then subtract off plugging in the lower bound. So far in this course, every integral we've done has been what's called a definite integral. Given some function little g of x dx from a to b, if the Riemann integral of this function exists, then it equals a number. And that number represents some area between the graph of y equals g of x and the x-axis. So whenever we compute a definite integral like this, the result is a number. We use an antiderivative in order to more easily calculate that number, but at the end of the day, what we've computed is some kind of area computation. There are other applications of integration, of course, which would compute volume, surface area, arc length, things like that. But whenever we have a definite integral, we're measuring something. There's another type of integral called an indefinite integral. Notationally, the difference is that we don't have bounds on an indefinite integral. So we just write this as the integral of g of x dx. Without bounds, that integral is equal to capital G of x plus c, where g of x is any antiderivative, and then plus c really is plus c, to represent plus a constant. So typically, if I were to write capital G of x for a specific little g of x, I choose the most basic antiderivative. For example, the indefinite integral of x dx would be x squared over 2 is the most basic antiderivative plus c. The antiderivative of e to the u du is e to the u plus c, where c is any constant. Therefore, what we have on the right-hand side is not a single function, it's actually a family of functions. It represents every possible antiderivative of the integrand. So these are two types of integrals. One of them computes a number, the other one computes a family of functions. Now, when we talked about antiderivatives at the beginning of this lecture, I said that there was no formula that you plug into in order to get an antiderivative. With differentiation, it's much easier. If I say sine of x squared plus 3x all over x cubed minus cosine of x, you can take the derivative. We have shortcut techniques. You could also set up a computation that gives you the derivative, namely you would take the limit of the difference quotient. Antidifferentiation is trickier, and in fact there are some integrals that we just can't compute by hand. For example, take sine of x squared dx. It's not a complicated integrand. We could certainly compute its derivative, right? It would be cosine x squared times 2x. You can't antidifferentiate this to a nice closed form expression built out of what are called elementary functions. You just can't do it. In the next lecture, we'll look at some techniques of integration to try to help us identify when we can expect to write down an antiderivative in closed form, but we can't always. So integration is one of those operations where we do our best to learn how to recognize antiderivatives, how to compute them by hand when we can. But in reality, for something like the integral of sine of x squared, we need other techniques. Sometimes it's just numerical computations. There are other ways to approach this integral, but you can't do it using just the techniques of this lecture and the next. I want to talk a little bit more, though, about what we can say about this kind of expression. Consider a similar function, f of x equals e to the x squared. You can try. Don't spend too much time trying to do this because it's not possible, but you cannot come up with a nice closed form antiderivative for this. So it's not like, oh, the antiderivative of this is e to the x squared divided by x squared plus 1, or something like that. You can try, but you can't do it. There's no closed form antiderivative built out of elementary functions that we can write down for this expression. Given that, the natural question to ask is, does this function even have an antiderivative? Maybe we can't write down an antiderivative for it because no antiderivative even exists. But going all the way back to the fundamental theorem of calculus part 1, one of the consequences of that part is that all continuous functions have antiderivatives. E to the x squared is a continuous function, so it has an antiderivative. In fact, it has infinitely many. Here are two of them. Let g of x be the integral from 0 to x of e to the t squared dt. This is actually an area so far function. It's computing the area under the graph of e to the t squared between 0 and the input x. It's a function. Given x, you plug it in, you get out a number. It's very hard to get that number by hand, of course, but numerically, we can calculate an estimate, and of course it does exist. And by the fundamental theorem of calculus part 1, its derivative is e to the x squared. So that's one antiderivative. Here's another one. H of x is the same type of expression as an area so far function, but starting at 1. Doesn't matter if you start at 0 or you start at 1, the derivative is still going to be e to the x squared. So these are two area so far functions, and by the corollary of the mean value theorem that we looked at the start of this lecture, if these two functions have the same derivative, then they better differ by a constant. So let's check that. What is g of x minus h of x? That's going to be g of x, which is the integral from 0 to x of e to the t squared dt, minus h of x, so that's the integral from 1 to x, e to the t squared dt. Let me flip the bounds on that second integral. So we can say that's actually plus the integral from x to 1 of e to the t squared dt. Now we can actually put those two integrals together because the upper bound of one is the lower bound of the other. And we get that g of x minus h of x is the integral from 0 to 1 of e to the t squared dt. This is a definite integral. It's just a number. And it does not depend on x. It's a constant. And that agrees with our corollary from the mean value theorem. So in fact, we can now say that e to the x squared has an antiderivative. In fact, it has infinitely many, and they would all look like these area so far functions. So while you can write down continuous functions, which are not big, they're not complicated, e to the x squared is not that hard of a function to actually write down. You can write it down, you can't antidifferentiate it to something nice, and yet it does have an antiderivative. Okay, so that concludes our lecture on antiderivatives. Again, in the next lecture, we'll go back to integrals that we can actually do by hand, and we'll look at some techniques of integration. Thank you for your attention.